All right, so let's look at this next unit on the rotational, which is talking about the energy and momentum component. So, right, the previous unit we talked about the forces and the kinematics portion, right? Forces, dynamics, the motion. Now we're talking about the energy and the momentum. Now, most of this stuff's very similar when it comes to energy. It's just when something is spinning, right? It's not moving in a straight line. There's different pieces moving at different speeds. We can combine it and say like, oh, there's energy in something that's spinning. So there's rotational kinetic energy. It's still kinetic energy because remember, kinetic energy is the energy of something moving. And when something is spinning, pieces of it are moving for sure. But it's caused by objects spinning around on an axis. So we separate this from what we learned in Unit 3, which is the translational kinetic energy, which is the energy of motion due to the center of mass moving at a speed. So now when things are rolling, they might have a center of mass velocity, so they'll have a translational kinetic energy, but they also might have a rotational kinetic energy. They may have both or only one of those things. But our general concept around work and energy doesn't really change. Work causes a change in energy. Rolling is a very specific case, and you have to be very careful on this. Rolling without slipping is a very common scenario that we have. And when you roll without slipping, there may be friction, but there's definitely no kinetic friction because when it rolls without slipping, it doesn't rub against the surface. Okay, so it's not kinetic friction. Okay, if it's rolling while slipping, then there is some kinetic friction because then what that means is the surface is rubbing against each other. So we can apply a relationship between the center of mass velocity and the center of mass acceleration to the angular acceleration and angular velocity. Now, if there's some angular acceleration or a change in the angular velocity, then there has to be some static friction because static friction is the only thing that's going to be exerting on torque when you have things that are just kind of like rolling without slipping on their own. So static friction usually acts as the torque to cause something to roll faster or slower. It doesn't do work on the object. This is a super important thing, is that static friction, because it's not rubbing against the surface, does not actually do work. So there's no change in energy when we roll without slipping there. All right, or at least the friction is not causing a change in energy. We still do conservation of energy. Okay, then we have angular momentum, and so there's a couple of things in conservation of angular momentum, which is kind of like we did in Unit 4. There's a similar angular impulse or linear impulse causes a change in momentum. Here, it's angular impulses cause a change in angular momentum. Now, for a system, the angular momentum is I times omega, the rotational inertia times the angular velocity, just like linear momentum is mass times velocity. It's very analogous. M is like rotational inertia. Linear velocity is like angular velocity. So very, very similar equation. However, sometimes we do a point mass moving at a straight line. And so this is the general form for angular momentum. What we do is we do r times the linear momentum, or mv, the r perpendicular to the v, and you can put the m in front, m is a scalar, or you can do m times r v perpendicular. And so the whole idea when you're doing something like this is to say like, hey, if I'm moving in a straight line, there's still angular momentum relative to an axis, and this is how we calculate it. Very similar to torque, right? So torque, in the previous unit, we took the component of r perpendicular to the force. Here you take the component of r perpendicular to the velocity, and that gives you how we go about calculating linear momentum. Okay, or we can do I omega for like a system. So changes in angular momentum has to be caused by an angular impulse. That's where this comes from. If there's if this angular impulse is zero, if this is zero, then we have no change in angular momentum, and that we call conservation of angular momentum. So conservation of angular momentum also used in collisions, just like we did linear momentum. When you have a collision, you may lose kinetic energy, so we do conservation of angular momentum or angular impulse to handle those kinds of scenarios. However, because angular momentum is not just about how fast it's moving, it's about the rotational inertia, it's entirely possible with single objects, but the rotational inertia is changing. And so that's in the case where like the figure skater is spinning around and they move their arms in, they're changing their rotational inertia, but there's no external torque, so we still conserve angular momentum in that scenario. So they spin faster because they reduce their I and increase their omega, right? So that's the other use of conservation of angular momentum that doesn't have a similar, like a collision like it was in Unit 4 when we did a lot of collisions between objects. So let's take a look at some problems here. Multiple choice questions. So here we experience external torque that varies over an interval of 5 seconds? Well, first of all, we have a graph, so we should look at the graph, and the y value of this graph is going to be the angular momentum. The slope is the change in the y variable over the change in the x variable, and the area is going to be the y variable times the change in the x variable. Now, this is not a formula we know. However, this part here should remind you of this equation. What caused the change in angular momentum is torque times time, so you can write that as torque, the angular impulse over that time. That cancels. And look at this. We find the slope is equal to the torque. So the slope is going to be the external torque on the system. So they each experience an external torque that varies over an interval of 5 seconds. Disk B has a rotational inertia that's twice of disk A, so that means IB is equal to 2 times IA. The graph represents the angular momentum of the two disks as a function of time. The average magnitudes of the net torques exerted at A to B are torque of A and torque of B, respectively. Which of the following expressions correctly rates the magnitudes of the average torques? So the slope is going to be the average torque. So the slope is going to be the torque. So in this case, when we're asking about the average torque, we want the slope of 2 points. Not the slope at a particular point, but of 2 points. And so we're just going to look at the slope of, let's see, this is object A. The slope from there to there is going to be the torque. And that's going to be the average torque because it's the slope over an interval, right? And so when we look at that slope, it's going to be 20 over 5, which is 4. And then for this guy, you're going to go from here to get this average torque over the 5 seconds. That slope is going to be 10 divided by 5, which is 2. So the torque from A is twice as much as the torque of B. And so torque of B is 1/2 of the amount of torque of A. So it's going to be C here like that. So that's a really powerful way, because it's not like I've listed out for students what does angular momentum versus time plot, and you memorize it. You just think about, well, the slope being the change in the y variable over the change in the x variable. So let's take a look at this FRQ here. So here we have a uniform rod of length L, mass M, is free to rotate vertically around a pivot. The rotational inertia of the rod alone around the center of mass is given as I. The system is pivoted at a distance d away from the center of mass and released from rest. Center of mass, because it's a uniform rod, is halfway, so it's L over 2. The system swings down under the influence of gravity until it reaches the lowest point. Let omega be the angular speed in the right. So this thing's going to rotate with an angular speed omega. Suppose the distance d is increased. Will the angular speed omega of the two-sphere rod system increase, decrease, or stay the same? Oh, actually, it's supposed to say the rod system. The rod. Increase, decrease, or stay the same. So how's the angular speed going to change when we do this? Well, we're going if we lift this up, what's going to happen is we're going to increase the rotational inertia. So if you move this point down here and move this thing down, we're going to increase the rotational inertia. We do increase the gravitational. Well, actually, so the biggest thing is we probably increase the gravitational potential energy, right? Because it's going to be swinging heavier up here. And then it's going to get converted into more kinetic energy afterwards. So I'm going to say increase, because it's going to start with more gravitational potential energy, because the center mass is now going to be at a higher location. And so it will end with more kinetic energy and thus be moving faster. Okay, let's derive and see what's going to happen. Derive an expression for the angular speed in terms of m, L, d, and omega. So we got to think about our reference point. So the reference point is going to be probably what I would pick as the lowest point, which is going to be the center of mass is located here, which is L over 2, which is going to be the same as this position here. Okay, so like, sorry, this is the center of mass. This is just a reference position here, because this is gonna be at L over 2. This is L over 2, and then actually, sorry, this is D. Sorry, let me write where the center. So the center mass is gonna be halfway here. This distance is D. So this is gonna be our lowest point, right? Now, what's going to happen, and what's a little tricky to see, is that when this thing, we got to think about how high is he above this point here. I know it looks like it's about halfway, but that's just by scale. Like, we got to think of this distance here is going to be L over 2 minus D to this endpoint right here. And this endpoint and this thing, this distance here is L over 2. And let's just mark the distances over here. This is going to be, this distance is L over 2 minus D. And this distance is also L over 2. Right? And so if these are going to be in the exact same spot, here and here. So maybe that's probably the easiest thing to do is look at the reference height as like that is there, and anything above there is going to be the gravitational potential energy. So I'm going to pick that as my reference height. And I know normally I pick the lowest point as my reference height, but I think this will be easier because I know that these two are at the same height in both figures. So anything below is going to be negative potential energy. All right, so that's something we did in Unit 4. So let's talk about our system being the Earth plus the rod. Because there's a change in height. So let's look at the initial energy. We don't have any kinetic energy. It's going to be released from rest. So the gravitational potential energy is going to be mgd here. It's going to be mgd because the center of mass is located d above where our h equals 0 is. Now, how about the energy over here? What final energy do we have? Well, we're going to have some kinetic energy, 1/2 I omega squared. Now, this I is not just of the rod. It's of the rod. This would be the I around the center of mass, but we'll talk about that. And then there's going to be some gravitational potential energy. Now, the kinetic energy is 1/2 I. Now, this I, because it's off from his center of mass, it's actually going to be by parallel axis theorem, I plus md squared times omega squared. And the gravitational potential energy, because he's a d below our h equals 0, it's negative mgd. Okay? And so by conservation of energy, that's going to equal mgd. We move that over, we get 2 mgd is equal to 1/2 I plus md squared omega squared. So multiply by 2, we're going to get 4 mgd divided by I plus md squared. And then the square root of that will equal omega. So that will be our derivation for the angular speed as that. So now we have to think about is here, derive an expression. Suppose the pivot is now placed at the center of mass of the rod. So now that's going to be d is equal to 0. Indicate how the angular velocity of the system would change in the right figure. So d is going to go to 0. It's not going to move at all. So if d goes to 0, then it's kind of like balance. It's going to have the same potential energy in this case, so it's going to go to 0. So our equation here is going to be 0 over I, which is non-zero. So 0 over non-zero value is going to be 0. So it's just going to go to 0. It will go to omega equals 0. So that's just telling you, and that makes sense, both figures are going to be the same because it's just going to look like this before and then it's going to look like this afterwards, right? So there's no conservation of energy. It's going to be perfectly balanced, right? So there's going to be no kinetic energy at the end. Okay, let's look at another one. A small clay ball of mass m slides across a smooth horizontal table with speed v0 and collides inelastically with the stationary sphere bob attached at 1. The clay sticks to the spherical bob, and the system begins moving in a circular path on the table, so it'll start moving in a circle. And as the bob continues moving in a circle, the rope wraps around a fixed pole, decreasing the radius of the circular path. The rope remains taut and acts perpendicular to the tangential velocity of the spherical bob the entire time. So the tension is going to be acting perpendicular. So it's going to wrap around until eventually at some point it's going to be moving with some other speed with a smaller radius. Suppose the mass of the clay ball m is increased while keeping mlv not the same. Well, the final speed of the clay bob system when the rope is wound increase, decrease, or stay the same. So during this entire motion, we have to think about it's a collision, so we should be thinking angular impulse causes a change in angular momentum. Now here, if we think about the system as being these guys here, we want to ask ourselves, as we're doing this, as they collide and as it moves around, oh, this thing should be sticking off on here. As it moves around, is there any external torque on the system? Well, there is a force tension here that's going to be perpendicular to it, right? But if we draw our R vector from there to there, it's not going to exert a torque because that tension, all right, is perpendicular to velocity. So that means that R vector is always going to be parallel to that force of the tension. And so no, there's no forces. And this is an aerial view. Okay. I didn't say this is a top view. Should have mentioned that top view on this problem. So there's not gravity. So we're like looking at it from above. Okay, so it's going to hit it. So there's no external torques on the system because there's no other forces. There's force of gravity, force of normal force, but those are not going to exert any torques around this axis of rotation right here. This is our axis of rotation, right? And so this is going to be 0, so the change in angular momentum is 0. Even when it's stuck together like this and moving around, again, the tension is going around this axis of rotation. Our R vector is always going to be parallel to the tension force. That's what this last statement is really telling you here. Okay? So there's no torque, so momentum is going to be conserved. So ultimately, increasing the mass increases the amount of angular momentum. So increasing m will increase the angular momentum of the system. And ultimately, and by conservation of angular momentum, we'll have a greater speed. Have a greater speed. Okay, so increase. So let's look at a derivation for that. What's the final speed v2? We'll call this v2 here of this thing afterwards, right? That's the v2 we would like to solve for there. Okay, so let's take a look at how that's going to work. We're going to start with the initial angular momentum. Okay, now this thing doesn't have an angular momentum. This thing does, and the way you calculate the angular momentum of a straight line is from our axis of rotation. We'll draw our vector, but we only care about the component perpendicular to the velocity. So we're going to decompose this into this component and this component. This component is L, and we only care about the component perpendicular to that velocity. So that's m v r perpendicular, which is m v naught, or actually this is little m v naught times L. So that's the initial angular momentum. Final angular momentum is just going to be I omega because they're stuck together, and this is the I total. The total angular momentum is the angular momentum of that guy, m r squared, plus the angular momentum of the bob, which is little m r squared, times omega. And so then we're going to have little m v0 L is equal to m r squared plus little m r squared times omega. And so omega is going to be m v0 L divided by mr squared plus little mr squared. And so that's going to be that part there. Okay, derive an expression for that. Instead of sticking to the spherical bob, suppose the clay ball collides elastically and bounces back to the left. How would that change the final velocity of the sphere compared to the previous scenario? So let's take a look at this. What we're going to do is we're going to import more momentum onto this guy, right? Because this guy, he moved to the right afterwards, right? So his momentum, angular momentum was to the right. But if he bounces back, his angular momentum is going to be the left. That's going to leave more angular momentum onto the sphere because the total angular momentum is going to start the same. So he's going to move faster to the right, and so he's going to end up faster. So this part, we would say the clay loses more angular momentum. Momentum by bouncing back. Giving the bob more angular momentum. And thus increasing its angular velocity. And I just realized something. They ask about the final velocity. We only solve for the angular velocity. We're supposed to solve the velocity v2. That is just v2 is going to be r omega, and the r being just little r in this case, so it would be r times this. So it would actually be r m v0 L over, we can factor out an r squared, m plus little m. One of those r's will cancel, so it'd be m v0 L over r times big M plus little m, like that. So that would be our actual answer for part B, by the way, because I solved for the angular velocity. And so last year we had to say, and thus the linear velocity. Okay, and that's that.